Welcome to SanfordFlipMath. This is PreCalculus, and we're starting Chapter 2. We're following the book PreCalculus by Demana, Foley, Kennedy, the 5th edition, which is from 2001. We are going to Section 2.1 starts initially with a little overview or review of polynomials, what polynomials are, and then talk specifically about linear functions and then quadratic functions. So just a quick reminder that is, of course, what what polynomial functions are. And I know that's fun to read. Basically, we're just saying that we're talking about some kind of a number, that's the a sub n, times x to the n, and to be a polynomial function, all of those exponents need to be non-negative integers. These are all just numbers that are coefficients. They could be fractions, they could be negative, they could be positive. And so basically this is just saying that a polynomial is any version of this. So an example might be f of x equals 3x squared plus 2x plus 1. That's a polynomial. G of x equals 3x minus 1 is a polynomial. The leading coefficient, the leading term is the term with the highest degree exponent. So the highest exponent out of the bunch. So for instance, the leading term for this first one is 3x squared. The leading coefficient would just be the coefficient part of that, or in other words 3. So for this second one, same idea, the leading term would be 3x and the leading coefficient would be 3. Just as a little contrast, let's do h of x, and let's say it's 1 minus 5x to the third, etc. And we'll just leave it at that. So the leading term would be the negative 5x cubed, and the leading coefficient would be negative 5. Now, here's something you're really not going to like, and that is, say j of x is, let's say 7x squared is still considered a polynomial. I understand that the word poly usually we think of as meaning many, or at least more than one. But this polynomial only has one term. This polynomial happens to also be a monomial. So it is a polynomial. It is also a monomial. It's still considered a polynomial because it still fits that little definition there. It just says that it needs to have at least one term. So n can be 0, n can be 1, so it could just be that, or it could just be this. It doesn't have to be a whole string. It can be any chunk of that. Okay, so 7x squared is a polynomial. It's a monomial. Its leading term, shockingly enough, is the only term. Okay, so each term is a polynomial, or is a monomial, excuse me, and its leading coefficient would be 7. Okay, you'll like this even less. That's a polynomial. It's a constant function, but it's still a polynomial. So the leading term is 7, the leading coefficient is 7. And then with all of these, you can talk about degree. And the degree is it's the highest degree out of all those terms. So it's the highest exponent for the variable out of all those terms. So this first one has a degree of 2 because it's 3x squared, and that's the highest exponent for a variable. This second one has a degree of 1. This third one has a degree of 3. This next one, degree of 2. This last one, well, where's the exponent for x? Well, that would be degree 0, because x to the 0 is 1. Assuming x is not 0, and 7 times 1, that would be 7. So in other words, 7x to the 0 is the same thing as 7, so the degree is that 0. Okay? Excuse me. polynomials can be classified based on their degree, and they have certain names. So for instance, if you just have f of x equals 0, the degree is undefined because there's not even a, 0x to the, it's not even 0x to the 0. In this one, it'd be like ax to the 0. So the degree is 0, and it's called a constant function because if you're talking, an example might be like y equals 5. That's a constant function because as I look at different x values, the y values are constant. They're all the same. Okay. This is linear, shockingly enough, because it makes a line, and we're more used to seeing this y equals mx plus b. And didn't want to do that. Sorry. That. And we're more used to seeing it that way. And of course, when we graph it, it makes a line. Okay. And quadratic, as you know from your history with math. So an example of this might be like 3x squared minus 4x plus 1. Quadratic is squared. And I mean, it's kind of a misnomer. Quad we think of as meaning 4. But in this case, it has to do with second power because, and it's really because we call this squared. And squares have 4 equal sides, blah, 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 4 congruent sides. So, worth noting that we can also classify polynomials based on the number of terms. So like if I have y equals x squared, that is a monomial because it is a polynomial with one term. Y equals x squared minus 2x is a binomial. Y equals x squared minus 2x plus 1 would be a trinomial. Okay, so again, this is all keyed in with prefixes that go with how many terms they have. So there's 3 terms, so that's a trinomial, like what I do down in the cafeteria, a trinomial. Okay, so you can classify polynomials based on the number of terms, the number of monomials that make them up, or by the degree. Okay? All right, moving on. All right, we are going to talk a little bit about linear functions. And this is something that you started working with maybe in pre-algebra, but really Algebra 1 is when you get into the meat of it. And so a linear function, just what we were just looking at a second ago, they defined it as something like this, which you are more used to seeing like this. Same thing, and this, as you know, is called slope-intercept form. Now, back in the dark ages, when I was doing this, we called it y-intercept form. Well, some people actually call it slope y-intercept form because m stands for slope. Obviously, m for slope, hello. So obvious from the Greek mountanis. Okay, I'm making stuff up now, sorry. And the b, excuse me, would be the y-intercept. Now, technically, the y-intercept would be 0b because the y-intercept is always 0 something. It's on the y-axis. All the x values on a y-axis are. There are other forms of equations of the line. This is the one that looks most polynomial-ish. I would also like to mention this is called point-slope form. It is one of my favorite forms, mainly because it is super easy to write from knowing a point and a slope. You don't need to know specifically the y-intercept. You can know an ordered pair and knowing the slope. That's enough to know point-slope form. And you can still graph from it. You can still graph from it. You can still write an equation. You can do everything with this form. Okay. Well, let's do a couple examples. Okay, and the examples that we're going to focus on are the ones that are a little more interesting, and that's writing equations. So like if I have 1, 5, and let's say negative 3, 11, we're going to write the equation for this line. So the instruction might say something like, write the equation of a line passing through those 2 points. Or it might say, write a linear function that includes those 2 points. Okay? Well, you need to know 2 pieces of information to write the equation of a line. You need to, okay, so you need slope and a point. Well, I have a couple of points, so that's not a problem. I just need a slope. Okay. Well, slope, as you recall, is rise over run. Okay, change in y over change in x. Rise over run, y's over x's, rise, y's, and thank you. How that rhymes? All right, 11 minus 5 over negative 3 minus 1. So this is going to be 6 over negative 4. I'm going to simplify that to negative 3 over 2. Okay, this is slope. This is m. Now, some of you would like to then do y equals mx plus b. Now, you are welcome to do that, especially if it does not specify a form. And so I know the m. Sorry, that just meant I got an email. So now the question is, how do you get the b? Well, in order to do that, we need to substitute a y value and an x value. And I need them to come from x and y that go together. Okay, so for instance, I could pick this lovely point, 1, 5, for instance. Now, could I have picked the other one? You bet I could. Doesn't matter. So the y value from that was 5. 1 plus b. Okay, and solving for b, negative 3 halves times 1 is 3 halves. Sorry, negative 3 halves. Add 3 halves to both sides, 3 over 2. Okay, well 5 is 10 halves plus 3 halves, and that all is going to equal b. So, sorry, I'll take that over here. b equals 13 halves. Now, I know some of you just had a hissy fit because I actually used fractions. Sorry. You could do decimals. There's nothing wrong with decimals. There's nothing wrong with fractions. Ultimately, the equation we write is y equals negative 3 halves x plus 13 over 2. Now, if you wanted to check this, the ordered pairs we started with need to be solutions. So you could actually take these ordered pairs, put in 1 and 5, and make sure it worked. Put in negative 3 and 11, make sure it worked, and by it worked, they have to be equal. Okay, and that's good. Now, if we were going to use point slope form, the one that I said that I was kind of partial to, okay, now I still need the slope. Okay, well, here's the slope right there. So the slope is negative 3 halves. And then what I need to do is do y minus a y value. Well, if you recall from up here, 1, 5 is a point. Let me make a note of it here. Well, this is x, this is y, so y minus 5, and then x minus 1. And the cool thing about it is, looky here, I'm done. Now, let's just do a quick little comparison. I had to find the slope for both of them. And then I need a point in here, and I'm done. Okay, compared to, I had to have the slope for this one, and then I had to do a little more work. You decide. Okay. All right, what I'd like to do is another problem, and it's going to look, in terms of process, it's going to be a little similar, but the change is it's not going to look the same. Okay, it doesn't start out looking the same. Ooh, did you see that magic just happen? That was exciting. All right, so what we're going to do is write a linear function f of x such that f of 1 equals 5 and f of negative 3 equals 11. Okay, so the question is, what's a linear function? Well, we already discussed that it's a function that could look like this, also known as this. Yes, it is even true. You could write it like this, and there's a but coming. Okay, the but is, if I'm specifying that I'm going to write f of x, then I don't really, in the end, I don't really want to write y. I want to write f of x, and it is not really good form to leave that minus y1 on the same side as f of x. So the thought is that we could adjust this just a tiny bit and write it in that form. Okay, so here are the options. Now, so a linear function, f of x, and then the other issue is, what is this other stuff here? What is all of that? And I guess the thing to remember is, you know, we're talking about notation that looks like this. So that means the thing over here is a y value, and the thing in there is an x value. So the thing over here is a y value, and the thing in here is an x value. So really, f of 1 equaling 5 is just that ordered pair. That's all that is. Okay. Similarly, this is a y value. This is an x value. This is an ordered pair again. Okay. So really, this is the same kind of problem that we just had a second ago. Okay. In fact, all right, I was being sneaky, or at least I thought I was. I tried to give myself away, though. Well, look at this information, 1, 5. Look at this information, 1, 5, negative 3, 11. Negative 3, 11. Okay, it's the same question. The only difference is when you get done, negative 3 halves over 2x plus 13 halves. You'd have to write f of x equals. Isn't that exciting? Or you could write f of x equals, nope, you guessed it. Okay, so I need a plus 5 on the end, x minus 1. Okay, so all I did was take this form from the last page and write it like that. And I just took this one and wrote it with an f of x. That's it. So it's the same process. Okay, and I'm not going to say much more about this at this point, but you know, let me just kind of again give you a quick setup. Okay, so if we said f of negative 2 is 8, and f of 1 is negative 2, then really all this means is negative 2, 8, 1, 2, and if I was looking for a linear function for this, okay, again, a linear function, then I'm going to do, I need to find slope, 2 minus 8 over 1 minus negative 2. So this is negative 6 over 3. And if I'm going with point slope form, which I love, y minus 2 equals negative 2 times x minus 1. So if I'm doing f of x, I would just adjust this a tiny bit, and that's fabulous. And if you prefer the other point, oh, sorry, that's an 8, minus a negative. So we would write this, sorry, that's part of the equal sign. So that's another way, and honestly, these two equations are equivalent, and you could even, if you wanted to, and you don't need to unless it specifically says slope-intercept form, You could even distribute this, so this would be negative 4x minus 4 plus 8. So here we go, negative 4x plus 4. All I did was rearrange it. And the same thing would be true here, negative 2x. Sorry, that's not SanfordBiffed. Sorry. This is real life. All right, there we go. Negative 2x, I'm just distributing. So negative 2x plus 4. Okay, and you could even do that here. Negative 2x plus 2 is the same thing. Okay? All right, enough about linear functions. We need to do one more thing, and that is quadratic functions. Now, today we're only going to do quadratic functions that are already in vertex form. Okay, so I'm going to remind you that vertex form looks like this. Okay, and there's also standard form, or sometimes this is called general form, but most of you are going to remember this as standard form. Okay, and they do the same thing. In fact, the A's are the same A. The only issue is this is vertex form. Vertex form is set up so that you can see the vertex, so that you can see the transformations from the parent function x squared. So you should just, we just finished this chapter about transformation. So if this is the parent function, and you know this thing went right 8 units, h units, this went right h units from 0, 0 for the vertex, and this went up k. Now we're assuming these are positive numbers and they could go down, etc. Then ultimately the new vertex is going to be at hk. So the cool thing about this form, cleverly called vertex form, is you can see the vertex. This one, not so much. You can talk about whether it opens up or down and how tall it has been stretched based on this A. You can also talk about the y-intercept from this form, but no vertex, and there'd be a lot of point plotting to actually graph it in that form. Okay. So let's just do a couple quick examples on how to graph from vertex form. Okay, so let's say we have something like x minus 2 squared plus 3. Okay, and the whole idea is the vertex is at, well, it's minus h, so really a positive 2, and then plus k, so that's 3. And again, the idea is if you thought about y equals x squared, it would have to shift right 2 and up 1, 2, 3. Well, if that vertex started at 0, 0, and now it's at 2, 3 because it moved right 2 and up 3, there it is. Okay, remember that whole inside inverse? There it is. Okay, so just a quick graph. If I go to 1 to 12, all right, so 2, 3. And again, the standard shape of a parabola has you moving left 1 and up 1, right 1 and up 1, and you could do the same thing with 2 and 4. If you go right 1, 2, and go up 2, 3, 4, etc. But I'm good with this. Okay. All right, so that's a quick thing to do from vertex form. All right, well, let's shake it up just a little bit, and then we'll be done. Okay, so let's say quadratic, again, in vertex form, negative 2, x plus 3 squared minus 4. Okay? All right, so the vertex for this one, inside inverse, so I'm going to say negative 3. Outside, do what it says, minus 4 or negative 4. So the vertex is at negative 3, negative 4. Now, a couple of issues here. This one is going to be upside down because of the negative. It's also going through a vertical stretch of 2, so when I just did my little thing where I counted over 1 and up 1, I'm going to have to go over 1 and up 2, or in this case, down 2. So watch this. Over 1 and down 1, 2. Over 1 and down 1, 2. And so my parabola is going to look something like that. Okay? You can actually go backwards. You can start with an actual parabola already, and if you know a point, you can write the equation. So for instance, if I had so here's my vertex at 2, 1, and let's say it's opening down, and let's say it's passing through this point 3, 0. Okay, I can actually build the equation based on vertex form rather simply, and I'm trying to boogie, sorry. Y equals A. I know the vertex is at 2, 1. And then the only problem is that I don't know A. But I do know another point. That is an X value. That is a Y value. So I can substitute and then solve for what I don't know. Oops, sorry. 3 minus 2 squared plus 1. And so this is 0 equals, well, 3 minus 2 is 1. 1 squared is 1. So this is A times 1 plus 1. Now just a quick little word of warning here. You need to do this multiplication. That's held together. You cannot call this A times 2. That's out. Okay, so I'm going to subtract 1 from both sides. Now 1 times A is really just A, but for those of you who are detail people, I'm going to go ahead and write it. I mean, this is kind of silly. But A is negative 1. Now we can substitute that in, and the final equation is, I know I lied to you, didn't I? I said I was going to just do the one more example. I forgot about going backwards. All right, so again, vertex in for H and K, substitute X and Y to solve for A. Oh, that rhymed. I'm just all excited, and I'm way out of time, which also rhymes with rhyme. Thanks for watching. We'll see you in class.